Hello and welcome to our lesson on natural hazards and in particular tropical storms. Today our three key takeaways are to be able to describe the characteristics of tropical storms, to explain where they happen in the world, and to try and justify why they happen in those places. So they can be really complex natural weather systems, but typically what are tropical storms? The tropical storm is a natural, powerful, low pressure weather system, and the key bit here is low pressure. Okay, so I'm just going to highlight that. So it's a key low pressure system. That's quite important. Tropical storms also have different names. For example, hurricanes, typhoons, and cyclones. The only difference between them is really the ocean that they're created in, the part of the world that they're created in. So, for example, from the Atlantic hitting around the Americas, that's going to be hurricanes. So, if we take this idea, um, first of all, we want to look at a few of the characteristics of these hazards. So, first of all, first thing to recognize is actually these weather patterns are enormous. Okay, you can see the size of them. Okay, they stretch out for a very large distance. Okay, so one of the first key things that we need to recognize is that these storms are huge in diameter, so they could cover a country quite easily, especially when they, for example, in this case, when they travel over the Caribbean. So sometimes they can be up to 300 miles wide, sometimes more than that, sometimes less than that. So you've got a really huge, massive storm. So that's one of the key characteristics that they have. You should be able to see, especially in the top picture, that the winds are rotating. I'll do this in a different color. Let's do it in red. So you can see there's kind of like a twist effect of the wind as it's all traveling, trying to get into the center. Same thing's happening here, it's just less clear, but it's trying to get into the center. Okay, so we have this kind of rotation. So these storms rotate, and in particular in the northern hemisphere, they are anti-clockwise. So this is just visually what we can see. Rotate anti-clockwise in the northern hemisphere. Brilliant. So we have two key characteristics, and then if we pick out one more that we can visually see, we'll do this in a green. So the upper point right in the center, oops, we'll change that to a green. So right in the center, you should be able to see a specific point, especially clearer in this one here. So another point is that in the center of the storm, they have what we call an eye. So the center of the storm, there is an eye. So we call this the eye of the storm. It tends to be the calmest part of a whole hurricane. And this will come onto after, but the eye is high pressure. So this is one thing that makes it a little bit different with tropical storms. Okay, so the whole storm is a low pressure system with air being pulled in that you can see with the red arrows, which makes it a low pressure system. As that air is pulled in over such a vast area, it rotates, and we'll look at why that is happening. And in the northern hemisphere, it rotates anti-clockwise. In the southern hemisphere, they rotate clockwise. And then right in the center, there is this high pressure area of calm, which is called the eye of the storm. So these are clear characteristics, things that we can see identified with these tropical storms. So huge, they rotate, they have an eye right in the center, and of course our final point is there are these huge storm clouds. So let's do this in blue. So they are large storm clouds. So with any cloud system, we are going to expect rain. Okay, so huge cloud systems like that, we're going to be expecting rain, probably a lot of rain. So we've got storms rotating, air's being pulled in, which creates our wind. They rotate anti-clockwise in the northern hemisphere, and the center, there'll be an eye of the storm, which is the calm part. And because they're huge storm cloud events, we can expect or predict that they'll create rain. Okay, so what we'll do, we'll move on. So we have some of the core basic characteristics of these tropical storm events, what they look like. What we'll do, we'll clear those, and then we will look at where they are formed. So what we can see is that from this map, you'll notice that the orange areas are where they are typically formed. So we can see that they are formed pretty much in and around these equatorial regions, okay, all across here. Now we can also see there's a rotation, or the tracks that the storms make. This one, it moves from the equator, goes across here, and then transfers up there. So their patterns can change. One thing that we definitely can see is that they don't form anywhere over land or in areas far away from the equator. So there'll be reasons for this that we'll look at, but what we'll do, let's just summarize a few of these key points. So first of all, they form near but not on the equator. So that's quite a significant point. They form near but never on the equator. And we'll look at that in a moment. They form around the tropics. Okay, so they need tropical climates to form. So never in higher latitudes. And the third point, they only form over water, so our oceans, never on land. So that's quite significant in terms of things that make them different. So before we move on, I'll just move this up and over here. So what we're going to do is we're going to look at the next part, which is this little diagram. So what we're going to do, is we're just going to try and explain why they form in certain places. So I'll just remove a couple of these markers. So The reason they never form on the equator is down to the Earth's spin. Okay, so we know these three things, those 3 points that we just mentioned about what they need to form. But basically, they never form on the equator because of this diagram. The air, or the Earth spins, fastest on the equator. It's got the greatest distance to travel. The Earth's effect won't be as strong if you go up towards the poles. The poles have a much shorter distance to travel because the Earth is thinner nearer the poles, so it's not as thick. So therefore they don't have to travel as far, so the air isn't moving as quick. Now all of the air on the equator is moving at the same speed. The only change happens as soon as you move away from the equator. This is where I'll add on a few arrows. This distance gets less and less and less. So the fact that that distance is becoming less means that the air is moving at different speeds at different points away from the equator. Now, of course, these tropical storms can be enormous, so therefore that difference in speed, because tropical storms can literally be about that size, that distance in speed will cause the storm to rotate, okay, to twist. Now this effect is what we call the Coriolis effect. And that is the effect from the Earth's spin. So that effect is created from the Earth spinning, and that's what rotates the air or deflects the air, okay? So we'll come to this again in a moment. Okay, so first of all, where are they formed? They're never going to be on the equator because they need that difference in wind movement, the difference in the speed the Earth is rotating or spinning. So they form slightly away from the equator, but they need to be near the equator to gain its warmth. They need to be forming over the oceans, over the water. They never form on land. So what we'll do, we'll try and pull this together a little bit before the end. We'll clear these drawings. So just to reiterate how they are formed, okay? So as we said before, they form near the tropics. So a key point here is that they need warm tropical water. So normally about 26 degrees. And what happens, this warm tropical water, which is only found near the equator, not on the equator, but near the equator, what happens to it? It evaporates. It evaporates, and that provides moisture that's going to rise up into our atmosphere. Okay, so warm air always rises. We'll just put a little note, side note across here. So warm air always rises. And this warm air that rises, it condenses to create clouds. So we'll put this as the next point. So warm, rising air, and warm air tends to hold more moisture, especially coming from the water. So warm, rising air condenses to create clouds. And that's the beginning of our storm event. Okay. Now we'll come into the spinning effect in again in a moment. So this creates our beginning of our storm. Now, our final point is that if the conditions are perfect, if there's constant supply of warm air, so constant supply of warm, moist air will allow the tropical storm to strengthen. Okay, and this increases all of the effects that it will go on to have. So it needs that constant supply. It can't have anything that's going to disrupt it or slow it or collapse the formation of that tropical storm. Okay, so there's a few key points there. So it needs warm water that evaporates to create the storm clouds. And as the storm clouds are created and the earth spins, you're going to start to see the air. In the moment the air rushes in to plug in the gap from all of that rising air, and our storm with that constant supply will strengthen. Okay, so in the top right, I've just got a diagram just to reiterate that point of the Coriolis effect that deflects the air to the center. Okay, so it always deflects the air, and that helps cause the rotation of the storm. So the final part is the movement of air. Okay, so we'll try and show this through this part here. If you imagine, we've got high pressure air to the left, the blue box, and we've got low pressure air to the right. Okay, now on the box on the left there is loads of air particles. Okay, so high pressure tends to have, just like if you pumped a tire with high pressure, you're putting more air into it. So there's more air in a high pressure area and there's less air in a low pressure area. That's why if a tire is low pressure, it tends to be more flat. Now what's going to happen is air will move from one to the other, always trying to find an equilibrium, okay, until there's a balance between them. This creates our winds. So this is what we experience as wind. Now, these winds will move from one area to the other, and over a period of time, what we'll see is that they're trying to basically plug that gap. But with a low pressure system, air is always rising, so air will always try to make its way towards the low pressure, okay? But as air is always rising and there are loads of high pressure zones, there might be high pressure zone over here, maybe one over here, and each time that wind is making its way from that high pressure zone, I'll just clear these arrows a second, making it from that high pressure zone to the center of that low pressure zone, trying to plug that gap. So we'll have wind coming in from here, maybe from up there, maybe from over here, and it's always trying to make its way to the middle. And that's what creates this rotation, this anti-clockwise rotation effect, which is why it's rotating in this bottom middle diagram as well. So there are diagrams at the bottom. And it's due to the air being deflected through the Coriolis effect. Okay, which is that box on the right. So I'll just add a quick note in here. So Coriolis effect deflects the air in the northern hemisphere to the right. It's in that right direction, okay? That's just something for us to bear in mind. As low pressure air rises, high pressure air is drawn into the storm. Okay, so it's the high pressure air, which you can see it's evaporating, it's rising up into the atmosphere, creating a storm event. Other high pressure air is being pulled in along the sea surface. Okay, gradually gets warmed up and the cycle will just continue. Okay. Now, because of the Coriolis effect, the air rotates as it moves to the center of the storm. And this will be the last point that we make, okay? And it's that constant deflection, that constant rotation, that will make it really, really difficult for the storm event to actually balance itself out. Okay, so it's that constant deflection right to the center of the storm that actually ends up creating the eye of the storm, this calm area. So everywhere right around the center, these will be, or right around the eye of the storm, these will be where the strongest low pressure winds are, okay? But because the air is constantly being deflected to the right, because of the strong rotation of the Earth and the Coriolis effect, there'll be a high pressure eye right in the center. So tropical storms are quite complicated events, but ultimately they happen because of a low pressure system, which is warm air rising through those tropical warm waters, and they need those tropical warm waters to create these cloudy storm events. And because the Earth spins on a huge scale, faster on the equator, slower as you move away from the equator, it causes that tropical storm to rotate. So what we'll do, we'll just summarize what we've got so far. So these are a few of the key points. So from our key takeaways, our characteristics of the tropical storm is that they rotate in an anti-clockwise direction in the northern hemisphere, clockwise in the southern hemisphere. They have an eye at the center of the storm. They can be up to 300 kilometers or more wide, and they're these huge low pressure systems. They form at, so where they form at tropical warm waters, so either side of the equator. And why are they happening? Because tropical storms are created through the process of evaporation from these warm tropical waters. And this creates our low pressure storm event that's rotated because of the Earth's spin, or the Earth's Coriolis effect, which causes air to deflect as it makes its way to the center of that low pressure system. So tropical storms can be quite tricky to understand, but those are a few of the core concepts that hopefully will make sense. Okay, thank you very much for listening. Have a good day.